You might think that it takes years of specialized schooling to become an engineer, but that's not true. A college degree is not what makes somebody a real engineer. In fact, even if your job title doesn't say engineer, you might already be thinking like one. You don't need to be a math or science prodigy. You don't need access to elite schools or insider connections, and you don't even have to wait until you're an adult to become a real engineer. My name is Josh, and this is Engineering a Better Education. First of all, I apologize if my voice sounds a little bit hoarse. Been sick the last week and still recovering. But I wanted to get on here and talk to you about something that's really important to me, which is what does it mean to be a real engineer? And as I mentioned, it's not the college degree that makes somebody a real engineer. You can think of a couple examples. One of them that I want to talk about today is Steve Wozniak. And maybe you've heard his name before, maybe you haven't. I'm sure you've heard the name Steve Jobs. Steve Wozniak was actually a co-founder of Apple along with Steve Jobs. But the reason I want to talk about Steve Wozniak is because he was the person who primarily, and you could maybe argue single-handedly, designed and built the first Apple I and Apple II computers. So whereas Steve Jobs is maybe the most well-known individual who founded Apple and perhaps the business leader, Steve Wozniak was probably the most instrumental technical designer on the computers. And like Steve Jobs, Steve Wozniak did not earn a college degree before co-founding Apple. Steve Wozniak began college, did about 2 or 3 years, but then dropped out in 1971, I believe, to co-found Apple. And then later down the line, he left Apple, and in 1986, he went back and finished his college degree. But the point is, you don't need a college degree to be a real engineer. Steve Wozniak was doing incredible designing and engineering work in the 70s before he earned his college degree in the 80s. So I think a lot of people would like you to believe that it's that degree presented to you from a university that makes you an engineer, but that is not true. And we'll talk about today what does make a real engineer. But I wanted to bring up that story because this is back in the 70s, and in some ways I would almost argue that a college degree was more needed back then to obtain the knowledge necessary to become an engineer than it is today. I mean, back in the 70s, they didn't have the internet like we do today. They didn't have easy access to knowledge and information and learning that we do today. So a university campus was maybe one of the only places where you could learn certain math and science and technical skills that are required for engineering. But today, you can learn that anywhere from your home with the device that sits in your pocket. So if Steve Wozniak could do it back then in the 70s, become a real engineer without earning or finishing his engineering degree, you can definitely do it today. I want to start by defining what is an engineer. And there are a lot of different definitions that people will use. If you look this up on the internet, you'll get a lot of different answers. The best definition that I came across for today's purposes is an engineer is someone who uses math and science to design practical solutions to real-world problems. We'll dive into this more in detail throughout the episode, and I'll bring that definition up and remind you of it as we discuss some important points along the way. But there's some key aspects in there. Using math and science to design. That's kind of like the first key point I want to highlight. Then the next is real practical solutions to real world problems. And we'll tie those things together. So math and science to design, practical solutions to real world problems. So in analyzing this definition, I want to tell you a story from my own life that occurred while I was attending college. There was a university professor in one of my engineering classes who the very first day of class asked us a question. He asked us, what does it mean to be an engineer? And specifically, what are attributes that engineers have to have that are unique to their career or profession? And you might not be surprised to hear this. The very first student who raised their hand said that an engineer is a problem solver. And at the time I was like, oh, that's a good answer. Yeah, like engineers are problem solvers. That's a good enough definition right there. But this professor really made us pause and think, because he actually shot it down and he said, no. He said, everyone is a problem solver. That's not something that's unique to engineers. And he said that every single job is a problem solver. And at first I was kind of like, wait, really? But then I started thinking about it and I realized that every single job solves problems. There's not a single job out there that I know of, at least, that doesn't solve problems. And let me just give you some examples. A janitor who works at a school, they're solving the problem of unclean bathrooms or floors that need to be mopped. And the solution to that problem is to clean the bathrooms, to mop the floors, etc. A teacher solves the problem, multiple problems. One problem is teaching children or helping them to learn the curriculum for that year or that grade. It's also to help the children manage their behavior, etc. A secretary solves problems. The problem is they are working for a company or an individual who needs to book appointments or manage their time. And so the secretary solves that problem by booking the appointments for the doctor or business leader, whoever it may be. And I could go on and on. Every single job is a problem solver. That's all we do as people. We encounter problems all the time and we seek to solve them, and we're constantly solving problems every day. So to say that an engineer is a problem solver is really not distinguishing engineering from any other career. And in fact, I would like to say that engineers are problem seekers, which is not so universal. So what do I mean by a problem seeker? I mean that engineers actively look for problems. They actively identify problems. So they don't actively create problems. That's not what I mean when I say they're actively looking for problems. But they are actively analyzing their own experience and the experience of others and asking the question, what is the biggest problem here? Or what pain points, what problems are people experiencing? And that's how they know what practical solutions to build, to design. They're looking for those real world problems. They don't just come to you as an engineer. Maybe if you work for a company and you have a boss who is telling you what problems to solve, but as an entrepreneur and an engineer, you really have to look for those problems. You have to seek them. So I want you to stop thinking of an engineer as a problem solver and instead consider the fact that an engineer is a problem seeker. And there are a lot of people and a lot of jobs also that are problem seekers. And by the end of today's episode, hopefully you'll realize that what I said in the intro, even if your job title doesn't say engineer, you might already be thinking like an engineer. And in some ways, you might already be acting and working like one. I also want to take a moment to make sure you know about my offer, which is a coaching program called Design a Product People Want. This coaching program is for teenage students who are interested in becoming a real engineer. The outcome of this program really is that they become a real engineer without waiting till after college and without waiting to become an adult even. And hopefully by the end of this episode, you'll realize that's very possible and a very worthwhile pursuit. And it's called Design a Product People Want because during this coaching program, the students will identify a problem that is worth solving. They will innovate a solution to that problem. They'll iterate their prototypes until they get a working solution, and they'll gain the confidence to sell or share their work with the people who are seeking that solution. So just as the name says, they will design a product that people want, and this is an essential skill to becoming a successful engineer and entrepreneur as well. So if you are interested in learning more about this coaching program, check out the link in the description below. That will take you to a Google form that you can fill out, and I will book a call with you and answer your questions, help you to understand more about the program, and hopefully my job to make it as easy for you as possible to decide whether this coaching program is a right fit for you or not. So once again, if you're interested, check out the link in the description, and I'd love to talk to you and teach you more about it. Going back to what we were talking about before, we've established that it's not the college degree that makes you a real engineer, and we've also defined what is an engineer. And once again, that definition is someone who uses math and science to design practical solutions to real-world problems. And I mentioned that exercise that one of my college professors had us go through on the first day of class, where he asked us what are attributes that are unique to an engineer, and how can we paint this picture of all the unique facets that, when they come together, create an engineer or define who an engineer is. I don't remember everything we talked about that day in that discussion about engineering, but I do remember some of the key points, and I've posed this question to myself now as a full-time engineer: what are the attributes of an engineer? And I narrowed it down to 5 attributes that I believe really define an engineer and distinguish what they do compared to everybody else. So the 5 attributes are that an engineer is analytical, quantitative, inquisitive, progressive, and systematic. We'll go through each of these 5 in detail. So the very first one is that an engineer is analytical. What does this mean? This means that an engineer draws conclusions from data. They analyze data. And data could be in the form of numbers. It could also be things that are a little more subjective. But what it means is that they look at data and they figure out what it means. They find the bigger meaning, the bigger picture behind the data. That's what it means to be analytical. And engineers are analytical. Engineers need to collect data. They do a lot of experimentation and a lot of testing. And when an engineer is doing research, that data isn't just necessarily used to validate an assumption. A lot of times it is used to discover new information. So discovery comes from collecting data from our real world. That's how the scientific method works, and that's how experimentation works. Collect data from the real world and figure out, what does this data mean? What are truths that can be drawn from this data? And not every job is analytical. A lot of jobs are, but there are a lot of jobs that don't necessarily require the collection of data and drawing conclusions from it. However, I believe every person working in any job can become analytical, and that they can use that to better perform their job. So I'll give an example. Maybe a security guard is not necessarily required to be analytical to perform their job. A security guard, their objective or purpose is to keep everybody safe, right? Maintain order and peace within an environment, maybe at a concert or something. And they don't necessarily need to analyze data and draw conclusions in order to do their job, but they could use that skill to enhance their job. So if they're working at a rowdy concert or something, they can, for example, look at the different zones of the concert and compare how rowdy each section seems, and then maybe station more guards or station themselves closer to a situation that is more likely to have a safety incident. That would be an example of collecting data. You're breaking up the concert into specific zones. you're rating each of those zones, giving them a number, and then you're drawing a conclusion that perhaps the zones that are most rowdy are more likely to have a safety incident. And so it makes sense to station a guard closer to those locations. So that's one example of how you can take a job that doesn't necessarily need to be analytical and apply that analytical engineering skill to enhance your performance. Okay, so that's number one, is analytical. Number two is quantitative. Engineers are quantitative. And what does that mean? It means that we use numbers, and we use numbers to measure things, and we use numbers to make something that's subjective a little more objective, a little more comparable, measurable. So this is where the math aspect of that definition, using math and science, and I forgot to mention this earlier, but the science piece is analytical. I mentioned that's what the scientific method is collecting data and drawing conclusions. So we've covered the science part of the definition. Now we're on to the math part of the definition, which is quantitative. So to be an engineer, you need to be comfortable using numbers. Numbers are logical and they're unbiased. They are a universal tool that can be used to transform, compare, and measure data. So going back to that example that I gave about a security guard, there was actually a part in there that was quantitative, which is, I mentioned that a security guard, if they wanted to enhance their performance on the job, could break up the concert arena into specific sections and then rate how rowdy or out of control each of those sections is. So the measure of rowdiness or out of control is initially something that's a little subjective, like, well, does that area of the concert look a little more out of control compared to this one? And you're maybe just kind of going off of a gut feeling of which one seems more rowdy in your opinion. But what engineers do a lot of times is take something subjective like that and figure out how to make it quantitative. How can we attach a number to this? So something that's common is coming up with rating scales. And there are all sorts of scales or rubrics that you can come up with that allow you to take something subjective and make it quantitative. Teachers are a really good example of this. Like an English teacher, for example, takes essays that students have written and gives them a numerical score, and they use a grading rubric for this. And once again, rating somebody's quality of writing is inherently subjective and somewhat opinion-based. But one way that you can kind of standardize that rating is to turn it quantitative using a rubric. You create descriptors for different categories or buckets and assign a number to each of those categories or buckets, which allows you to create a more unbiased overall picture of the quality of that essay or writing. So that's an example of thinking like an engineer, taking something subjective and making it quantitative. And then there are things, of course, like measuring length, weight, whatever, that is already quantitative in the way that we use it every day. But what an engineer needs to be able to do is figure out how to transform that data, maybe summing together measurements, taking an average, and lots of other cool math tools that we won't get into today. But that's number two, quantitative. Number three is inquisitive. An engineer is inquisitive, and that means they ask questions. They're question askers. An engineer is constantly challenging assumptions, challenging the system, asking questions. They don't just take things for granted because it was told to them or because this is the way it's always been done. By the way, if you ever hear that as an engineer, if you ask a question and someone says this is the way it's just always been done, that is not a good answer to continue. That's not a good reason to continue doing something and not a good answer to that question. And in fact, a lot of times that unveils an area of opportunity. If people are doing something because it's the way it's always been done, there's probably a better way to do it. So just a little plug there. And as I mentioned, a good engineer is constantly asking questions. First of all, they may be asking the question, what problem is worth solving? What problem or pain point do people have that I could design a solution for? That's the first starting question that an engineer would be asking if they're designing a product from scratch. But then as you get into the design process, you ask a lot of questions like, what solutions have people already come up with? How did these solutions fall short? Why does this process work the way that it does? To be a good engineer, you need to constantly be asking questions. Once again, not everybody asks questions in their job or line of work, but they could enhance their performance if they become more inquisitive. I'll go back to the example of a secretary, for example. They're going to ask questions to clients that they're booking with, or patients who come into a hospital. We'll talk about maybe a secretary at a hospital. They're going to ask the patient questions and get an appointment booked with the proper doctor. But the way that a secretary could enhance their performance and think more like an engineer is to challenge the system by being inquisitive. For example, is this software that we're using to book appointments really meeting our needs? If there is some kind of hoop you have to jump through every time you book an appointment and you're noticing that you're running into issues with your calendaring system, maybe double booked appointments or something like that, you could ask the question, why is this happening? Is this software meeting our needs? What can we change to improve our booking system? And that's what thinking like an engineer is. That's just a simple example, but I hope you'll consider how you can become more inquisitive and challenge the system more. There are opportunities all around us, and if you ask the right questions, you'll uncover those opportunities and realize that you're sitting on a gold mine of engineering opportunities. So that's number 3. An engineer is inquisitive. Number 4 is that an engineer is progressive. This relates a little bit to the last one. I mentioned that if you're inquisitive, you challenge the system, you challenge the status quo. And if you are progressive, and what I mean by progressive is always seeking progress and improvement, seeking change in a way. An engineer doesn't seek to maintain the status quo. An engineer seeks to progress the status quo in a sense, to progress kind of the baseline level of technology, solutions, systems. Once again, not everybody is progressive. Some people want things to stay the same. They want to maintain the status quo. And some people just aren't thinking about it at all. And if I'm going back to the example of the secretary working at a hospital, it could be easy in some ways to maintain the status quo, keep everything the same, keep using the same systems to book appointments. But if you want to think like an engineer and once again enhance your performance, then you should be thinking progressively. Think about how can we improve the system that we're using to book appointments. And like I said, being progressive falls in with being inquisitive. They both challenge the system and look for change and improvement. So if you want to be progressive, you need to start by asking questions and figure out where are our problems and pain points that we're experiencing, or maybe that a potential customer is experiencing. So that's number 4 is progressive. And number 5 is systematic. Engineers are systematic. They use systems to design products. They also design systems. So what does it mean to be systematic? A system is a repeatable process or set of steps that produces a specific outcome. So what it means to be systematic is that you create a solution that doesn't just work one time. It's not a one-off lucky solution that solved a problem for one person one time. A good engineer designs a systematic solution that anyone can use. Right now, I'm working as on the manufacturing side of engineering, and a good manufacturing line is one where you can take anybody off the street and have them work on your manufacturing line, and you'll get the same quality of product as someone who's been working there for a long time and has a lot of experience. And that's because you want a system or a process that's repeatable, that is systematic. You give it a certain set of inputs, and you can be confident that you'll get a certain set of outputs every time. Not everybody is systematic, but once again, becoming systematic will help enhance your performance and help you become more like an engineer. I'll use the example of a delivery driver. So when a delivery driver first starts, their route is most likely going to be unfamiliar to them. They might not know the best route to follow. They might not know in what order to deliver the packages that would be most efficient. And so their first few times on the job are probably not going to be very systematic. They're going to be maybe a little chaotic, going from one place to another. But over time, as they maybe do the same route or do the same job, they likely will develop systems, and they'll know that if I go to the delivery locations in this specific order, it tends to be faster. Or if I tend to organize the packages in this specific way, they're easier to find and deliver. So you might see some delivery drivers who in general are not very systematic, and some that are systematic. And what you'll find is those who develop and follow a good system are going to be more efficient and have a greater output than those who don't have a good system. So engineers, as I mentioned all the time, are following systems, and engineers are also developing systems all the time, whether it's a manufacturing system, manufacturing process, or a systematic solution to a real world problem that the customer has. So that's number 5, is systematic. And I want to tie this all into the definition that I mentioned at the beginning, which is an engineer is someone who uses math and science to design practical solutions to real world problems. Real world problem means that this is a problem that real people have, and probably a lot of people have. And this is where the systematic piece ties in really well. To create a solution that works well for a lot of people in a lot of different situations and cases, your solution needs to be systematic. And once again, that means that if you put in certain input, you can be confident you'll get a certain output. So that's the real world problem piece. And if we go back to the design's practical solutions, a practical solution is not just something theoretical. It's not being a theoretical scientist or physicist, though those things are really cool and they help progress the art of engineering. But a practical solution is something that can be applied to solving the problem at hand. And I think this ties in really well with the progressive attribute. In order to progress, we need to be delivering real results and real practical solutions that can be used and applied to the problems that we're solving. And then, of course, we covered the math and science piece, which we tied in with the analytical and quantitative aspects of an engineer. Analytical tying in with science because you're using the scientific method, and quantitative tying in with math because you're utilizing numbers. And I guess the one that I haven't quite tied in yet is the inquisitive piece. And inquisitive, I think, goes back to the real world problems and also the practical solutions. Because if you're inquisitive, you're challenging the system, you're uncovering those problems, and you are asking questions that allow you to arrive at a practical and robust solution. That's what I have for today, and that's how I look at a real engineer. And hopefully, through listening to today's episode, you've realized that maybe you're more like an engineer than you thought you were. Maybe you're a school teacher or something. I had this conversation with my wife, and my wife realized and told me that she is an engineer because she uses all 5 of these attributes all the time in her job. She's not content with the status quo. She is always asking questions, challenging the system, figuring out how she can do her job better, how she can create systems that will better serve her needs and her students' needs. And teachers are, once again, quantitative. They figure out how to measure things so that they can compare performance and allow students to measure their progress and performance. So I hope that you have recognized that you're more like an engineer than you thought you were. And if you ever felt discouraged about becoming an engineer, felt like it, once again, takes years of specialized schooling or access to insider connections, or that you needed to wait until after college or wait until you're an adult to become a real engineer, I hope you've realized that's not true. If we go back to the story of Steve Wozniak, he actually, as a teenager, was designing some of these computer systems on paper before he physically created them, the Apple I and the Apple II personal computers. He started before he had his college degree and before he was an adult even, and you can too. If you enjoyed today's episode, I invite you to leave a comment below answering the question, what is your career or job, and how do you apply engineering attributes to your job, and how has it made you more successful? I also invite you to like and subscribe if you've enjoyed this episode, and I look forward to talking with you soon.